I'll be recording this lecture, okay, just in case some of you may have a connection problem or may not be able to access WebEx. All right. So let me know if you have any problem. Okay. I'll be recording this session. Okay. Okay. So like what I mentioned, we are actually looking at robot control. Okay. And so most of you would definitely have come through the subject or this topic on control system, right? I'm sure most of you have done control systems, okay? Or any form of courses related to control theory, okay? So in this course, of course, it doesn't do justice to go through the subject of control itself in just 2 or 4 lectures, okay, 2 weeks of 4 lectures. But what we're going to do is to make it relevant for the context of robotics. So how is control system relevant to the context of robotics? We're going to look at how we design the right control strategy for that. Okay. Right. So from a high level representation, I believe we have gone through this last lecture. We see how it is relevant to robotics. In fact, if you look at robot system, you can look at it as a plant. Okay. If you kind of learn this in your control class, this is like your plant. Okay. So this is your robot system. Okay. It also be like your plant. Okay. Let me just change the color of this. Maybe this could be your plant using the control theories terminology. So this is nothing but your robot system. Okay, your robot system. Right, and then the problem here now is to create a controller. So the central problem that we are going to define is to be able to obtain a desired motion profile, okay, by inputting the appropriate input. And in this case, in the case of a robot, it could be joint torque. Okay, so imagine if you are having a multi-linkage, multi-body dynamic system, all right, which is your manipulator arm. Okay, so you're going to design a controller that will create certain motion profile, right? So you're going to design a controller that will create a motion profile. Okay, so this is your motion profile. Okay, and you go about doing this by putting in your top, right? Maybe let me okay, your joint top. Okay, and so of course you hope to achieve a desired profile. Later on, we will come back to look at planning. Okay, so it is actually at the planning part, okay, the robot planning part, that you come up with the desired trajectory. So what kind of motion profile you would like to have. Okay, so that is robot planning. And we're going to do this later. All right, in the lecture after your midterm. Okay, so that is a central question we will ask when we talk about robot control. Okay, so now that we have defined the control problem, okay, the next thing is to answer the how question. How do you go about designing this controller? Okay, and if you remember last week we talked about 2 approach, the open loop and the closed loop system. Okay, so one with feedback control, right? Okay, so what happened here is that if you look at the high-level representation, you are going to design this controller that will tell you what kind of input to send into your system, okay, so that you will have a state that you desire. All right, so one way is to make use of the governing equation, okay? In this case, the equation of motion that we have learned earlier on in dynamics, right? Remember robot dynamics that we did in the last 2 weeks, okay? If you analyze or model the robotic system, you can actually work out the relationship between the motion and the force or torque that is causing this motion. Okay, so that is a branch of mechanics we call dynamics. Okay, so dynamics is interested in dealing with the motion of rigid body or even a system of multi bodies. Okay, where we relate the motion with the cause of it, the torque or the force that causes the motion that actually create this motion. So we come out with this equation, the dynamic equation. Okay, so this is going to be useful because now for given desired this motion profile, theta d and theta dot d and theta double dot d, okay, we can find the kind of how, or in this case, force or torque that is required to create this motion profile, right? So remember now we know our tau, okay, for the given theta, right? Okay, so I'm just circling a few representative ones, right? So we are relating motion and torque in this case. Okay, so this is the relationship between them. Okay, and if you know this relationship perfectly, you can actually put this into your controller. Okay, so whatever motion profile you want, theta d, theta dot sub d, theta double dot sub d, we can make use of this governing equation or this dynamic equation to work out the correct torque that can create this motion. All right, so this is what we call open loop. And I hope that this is obvious enough for you. Okay, you probably can tell that what we are doing here, okay, it is not sending anything back to the controller, right? So this is open loop. When you don't send anything back to the controller. So the controller, the output of this controller or the input to the system, tau, okay, this tau here is going to be independent of our state, the robot state, okay, in a more technical term. Okay, so this is independent of the robot state, right? Or in other words, it doesn't care what happened to the robot. Okay, you just make use of this equation of motion to find out what kind of tau to set it, right? So you know that this is good if, of course, you have a perfect knowledge of the model, ideal case where there's no external disturbance, and you are sure of your relationship between the tau, between the torque and the motion. So that way, open loop could be a feasible way, feasible choice, but a lot of time that is not the case. Okay, you will actually need your closed loop system. Okay, that is, you actually need to feedback the state of the robot. So in this case, your state here, robot state. Okay, and you are actually going to send it back. Okay, so if you have a sensor or many sensors or just a sensory system that can send this state back to the controller. Okay, so this how here, okay, the top now is going to be affected, okay, by your feedback. Okay, that is updating it. Okay, so you are actually sending in some feedback to your controller. Say, for example, the error, sending the measurement Y. Okay, so this, of course, maybe your theta dot and theta double dot. Okay, this makes sense in transpose here. Okay, transpose saying that is a column, right? And then you get a measurement. Okay, sometimes you need to do calibration and you need to have some way of filtering the noise to reduce uncertainty, etc. Right? So this entire thing is known as closed loop system. And so we, in our last lecture, we explore a few different examples and why sometimes it is better to just use open loop and why it is better to use closed loop system. All right. So we summarize the overall takeaway in our last lecture. All right. The only difference is just that when we have a closed loop system, okay, we are looking at feedback from the sensor of our actual state of this plant here. So using a control terminology, okay, this is what we are looking at. Okay, the controller, the plant, and we actually have sensor to feedback the actual state to the controller. Okay, so we actually see this two main approach of control, and in this class, of course, we are going to look at feedback control, which require a little bit more attention. Doesn't mean that it is always the best thing to do, but it is more sophisticated and require some knowledge so that you can build or develop some robotics application robustly with this approach. Okay, so we've seen most of the stuff on control. Okay, so how do we put it into the context of robotics? So let's make this relevant. In this case, we know that in your robot, especially the manipulator arm, you will need to control the motion of the link, right? And so that is where you use joint control. Okay, so if we have a manipulator arm, okay, so that in this manipulator arm, you're going to have a few links, right? And there are joint as well. Okay, so you can put in, okay, say these are rigid body. Okay, each of this link, including the end effector, okay, you can look at them as rigid body. So this is actually a multi-body dynamic system, and the link will move with respect to each other, okay, or relative to each other, okay, with this joint torque. If you actually have some joint torque here, power 1, power 2, okay, of course you can have end joint, okay, in this case, let's say we have 3 of them, and of course it's going to create some motion. Okay, next XX. Okay, nice well. Okay, and each of these joint would also have their motion profile. I will put a 3 subscript to stand for the third joint. Okay, and of course, this you have already learned using your kinematics how you can relate the workspace and the task space. Sorry, the joint space and the task space. All right. So this is your joint space. This is your task space. All right. Okay. So how you relate this? This is kinematics. Okay. Your kinematics. All right. And so what you're going to do now is to look at each of these joints individually. Okay. So now these are just individual joint. Okay. And because let's say there's a motion here. Okay. This is one. Okay. And so you're going to create a control system, or you're going to design controller that will help you to achieve certain theta dot theta double dot one. Okay, or in the subscript of one. All right. So that is joint control. Okay, so I'll just put this joint. Okay, so that is the idea. Now, from here we will see a few components. Okay, just now we look at a higher representation, higher level representation of the entire thing. So you basically only have this controller to your plant, which in this case is really kind of like your robot. But you will see that it can actually means the entire, just one single actuator or something that you are interested in controlling. Okay, so you look at this plant. Okay, so that is the simple idea, and of course, you can send in with your sensor to your controller. Okay, to update the controller. So that is the high level representation, or I will put it as higher level representation. Okay, this is a higher level representation. And if you look at what is really inside, okay, you will see that there are actually this motion that we really want our link to be taking. Okay, or rather the motion that we want our link to be taking is defined here, but in this part here, this is the desired motion, the target. We can look at this as a reference or the set point reference. Okay, and this is of course the actual state. Okay, so how this entire thing works is such that usually we have actuator and mechanical transmission to actually implement this motion. Okay, so actuator like motors can have motors. Okay, but how do we actually command this motor to come up with the right motion? Okay, we can actually send in signal. Okay, so our joint controller, okay, the joint controller that we're going to design here, okay, will tell us the kind of signal that we need to send. Okay, it's going to tell us the kind of signal that we'll have to send. And usually this signal doesn't power the actuator directly. It doesn't kind of power the motor. Okay, it go through a motor driver. Okay, so you can have sometimes we call this driver. Okay, in a way, it kind of amplify the signal to come out with the right power. Okay, so your VI, of course, is the product of it is the power, and it's going to drive this motor. Okay, and this motor don't usually directly drive the link itself. Okay, it go through some transmission mechanism or some mechanical transmission to create that motion. Okay, so if it's a closed loop, it's going to have joint sensor. Okay, so joint sensor sometimes it could be encoder. Okay, I'm just giving an example. Okay, that will measure the actual motion and feedback to our joint controller. All right. So if we look at this architecture more, if we look at this architecture at a closer detail, okay, we will see that this is how a single joint can be like. Okay, a single joint. Okay, of the manipulator. Okay, so now we have a single joint of the manipulator. Okay, so this is joint. Okay, so this is going to be the joint, and it's going to carry the link, and it's because it's attached to the link, is carrying the link. That will be loading. Okay, the inertia of the link, all the dynamics that is related, friction, drag force, etc. Right, and so we're going to look at a few important components. Okay, the sensor, okay, that's one, and the actuator, okay, and the transmission mechanism. Okay, so maybe in some textbook they will define the entire actuator as the one that also include your transmission mechanism, right? So from here, basically actuator is something that act on the plant to kind of create a change. Okay, so in this case, we're going to kind of look at it as the motor, okay, that is driving the motion. All right. So taking a look at the sense, the various options in sensing the actual state of our robot. Okay, we see that there are a few types. Okay, we could be doing position sensing. Okay, in fact, we're going to do position sensing and force sensing. Okay, if we were to control the motion or even the force. All right, because in robot, a lot of times you're expecting it to do mechanical work, which involve the product of force and displacement, right? So position sensing is important, kind of like a fundamental if you are doing a closed loop feedback, or rather feedback control for a robot. Okay, so you can actually have linear sensing. Okay, you can have angular sensing. All right. Let me just. Okay. So you can have hang on, my screen is all right. I guess it's fine now. Okay, so you can have linear sensing that kind of track a linear motion, and your angular sensing. Okay, angular displacement sensing. So in this case, what you see here is an example of an encoder, rotary encoder. Okay, so in this case, it's quite common to have this quadrantial encoder. Okay, quadrantial encoder. So how this basically sense the position is through relative motion. So it's not going to give you absolute motion. You kind of need to read the change in the state. Okay, here the state as this coded ring is being rotated, okay, it will change from one state to another. So if you have a reference, you will know how much it has actually moved with respect to that particular reference by tracking the changes in the. So you can also have this range sensor, range sensor. Okay, so when you fix it with respect to a particular place, okay, you can actually track, okay, the distance, okay, between these two things, right? The transmitter of the laser for this case. Okay, you're gonna find this. All right. Okay. So we also have force sensing, right? So you can use strain gauge and you can use load cell, okay, to do the force sensing. So sometimes you attach this sensor to one link and the other part of it to another link. So these two parts, they are relative, um, say, change in the strain can actually um, be transformed into potential different, okay, different in the potential to give you signal. All right, so with a calibrated sensor, you can actually work out the force or the torque that is subjected onto your sensor. All right, so those were the force sensing, including your position sensing. So those are your sensors. Okay. Now we're going to look at actuator, which is another important component, right? So in this case, we're going to look at motors, right? So they are devices that power the motion. So you can have all kinds of different actuators. Okay, you can classify them based on the principle of how they generate the force, the torque, okay, and the kind of motion that they are producing, right? So the principle of force torque generation, okay, we have a few uh, different type of motors or actuators. We have hydraulic, we have pneumatic, we have electric, right? And for motion, we're going to look at rotation and linear, okay? So of course there are some motion of vibration, reciprocation, okay, free form motion as well, okay, but we won't go too much into detail on that. Okay, so what you see here, this is actually a pneumatic. This is a pneumatic motion. And this is probably hydraulic, right? And this is electric. Okay. So the different actuation principle, okay, is usually considered for different robotics applications. So when you are designing a robot application or solution using robotic device, okay, you kind of want to think of the different principle of actuation, right? So usually for heavy duty stuff, something that create high torque directly without too much transmission mechanism, okay, a very powerful actuator, you are usually looking at this hydraulic actuator. So you will see hydraulic actuator for industrial robots, okay, very often. So like this bulldozer. In fact, this is using hydraulic, but the problem here is, of course, sometimes it get a little bit dirty. Okay, you need to kind of it's a lot harder to maintain. but it can give you very powerful or high torque without having any other intermediate um, this transmission mechanism. Okay, so you can actually do direct drive with high torque. And for usually flexible motion or flexible configurations of robotics, okay, robots. Okay, a lot in soft robotics, you can use pneumatic, okay, pneumatic actuator. All right, so that actually allow you to kind of do flexible way, okay, because it's using air. Okay, most of the time there are gases inside all this soft body. All right, and electrical motor is actually very easy to control and implement. Okay, so the ease of interface is um, one of the main advantage of electric motor. Okay, so some of this robot project that you use, okay, you have all these motors. Okay, electric motor. Okay, in fact, these are integrated servo motors. Okay, so they will already have sensor inside. Okay, so they also include sensor and a control or feedback control system inside, right? So this is really integrated. Usually these are integrated motors or actuators, right? Okay, so those are actuators um, based on their different principle in generating the motion. Okay, and the kind of motion that they generate or the nature of motion that they generate is also important consideration. Okay, important consideration for designing a robotic system. Okay, so for example, if you want to do a 3D printer, okay, say in this case, this is maybe a 3D printer, right? Okay, so you just want simple Cartesian workspace. Simple Cartesian workspace, you can use linear actuator, right? So in this case, we are not saying that the motor is directly doing a linear motion directly, but of course there are some transmission mechanism that make the um, actuate the entire motion linear. Okay, so say for example, this stage here is moving in this way, a linear motion. Okay, so this is actually a stage, a translation. Okay, so a translation stage, it usually have a rotating motion. That the model that they use in most of the case, in most of these cases, are actually rotary motors, but they are attached to this worm gear. Okay, so when they rotate, the shaft will actually rotate this screw. Okay, with screw thread that will push this stage to move in a linear fashion, right? So that is transmitting this motion into linear motion from angular to linear. All right. And so sometimes you want, say, continuous circular motion. Say, for example, if you want this robot to be, yeah, we'll just draw an axis. Okay. So, for example, in this case, you have this robot rotating. The wheel is rotating. Okay, so you kind of need to the axis. The other side of the wheel is also rotating. Okay. So the wheel of a robot So we can actually use a rotary motor to make this robot move. But of course, eventually, you know that the robot can actually also move in a straight line, okay, by controlling the speed ratio between the wheel. All right. Okay. So let me make sure that I'm fine. Okay. So we're going to take a closer look at electric motor. Okay. So this is going to be DC motor. Okay. Later on, we will actually do a modeling of DC motor. Okay. This armature motor. All right. How we actually go about controlling the motor. Uh, Before that, we will actually need to look at the modeling of our DC motor. Okay. But of course, there are more than this DC motor. You actually have stepper motor. You have alternating current AC motor. You have ultrasonic motor, and you have piezoelectric. Okay, a lot of time we use this in the last two very common in medical application. Okay, sometimes you don't want the electromagnetism to interfere with other medical device. Okay, like in the magnetic resonant imaging system, MRI system. Okay, you don't want the motor to kind of disturb the control of the entire system. Okay, and because the MRI machine is actually a big magnet, okay, so it will actually suck the motor when you put it very close to it. Okay, so we sometimes use ultrasonic, and piezoelectric will be for vibrating motion. All right. So we're going to take a closer look at DC motor. Okay, so later on, when we do the modeling of this electrical system, the modeling of this electrical system, okay, we will be able to design the controller to do the necessary mechanical motion. So for now, let's take a very brief look at the principle of or the physics of this DC motor. And I'm sure most of you know this probably quite well. So just a very quick, for the sake of completeness, to show you what is actually inside. Okay, the architecture. All right, so you're actually looking at this DC motor. Okay, in this case, the shaft will be the one that is rotating, okay, with respect to the stator. So the stator is going to be fixed. So this part here is going to be fixed to a particular body, okay, and of course this you're going to attach this, okay, to a link, the center of gravity here. So this is kind of like your link. Okay. So this is maybe if this is link K, this will be K minus 1. Okay, and so you will have magnetic field created by the stator magnet. You can have magnetic field going from the north, south. Okay. Right, so this is a magnetic field. All right, so you know that it will actually, when you send in current, okay, when we send in this or when the armature circuit actually draw a current IA, okay, it creates this lens force, okay, BQV, okay, F equal to BQV, Okay, so if this magnetic field is right, this part here, of course, is your current. This part here is current, right? And this part here is your magnetic field. Okay, and as you see that you will actually create a torque that will spin the shaft. All right. So that is roughly how your motor will spin. Later on, we will take a closer look at this. All right. So today will very much be introductory material. I know last week we talked about the open and closed loop feedback control, and then we say that we're going to look at modeling of the system before we move into second order system and then design controller for second order. Okay, but because we are doing online for the time being, so I thought it would actually be better to talk about the introductory material first. Okay, and then we will move on to that. Hopefully, if we can start in-person lecture later on. Right. So for transmission system, okay, so we have seen how the motor works. Okay, most of the time, they don't drive the link directly. Okay, so the motor don't usually drive directly. Yeah, for most of the robotic project, yeah, maybe I will not confuse you with that. But a lot of time it is important. What I'm trying to say here is that it is important to understand the transmission mechanism between your motor and the load that it is driving. Okay, so in this case, there are some example. Like say if we attach to a motor here, this gear, the shaft, okay, motor shaft. Okay, so the shaft of the motor, as we saw earlier on, okay, this shaft here will be rotating. Okay, so it's going to rotate this gear, and let's say if you have a load here, I'll change this. So this part here is driving the load. So your shaft doesn't directly drive the load in a linear motion. Okay, it rotates this gear. Okay, in this case we call this pinion. Okay, this part here is your pinion and your rack. Okay, so this is a rack and pinion mechanism. Okay, so you drive the motor rotate this gear, and then the gear will actually pushes this rack linearly. All right, so that is how you do the transmission, and of course you can have something like this as well. Okay, there are many different mechanisms. This is you having a worm gear, okay, that rotates a nut, and then when you restrict this rotation, it will actually do a linear motion. So this motion here is linear, okay, but this motion here is rotation or angular. So why do we need a transmission mechanism or your transmission system? We actually talked about this earlier on. Okay. Okay. So one reason is that we need to do speed reduction or torque increment or vice versa. So the speed torque relationship is usually inverted if you have a constant power. Okay. And so sometimes you want to have higher torque. Okay. You can do so by doing speed reduction, or you want to have a faster speed, okay, then you will have to reduce, you will have to bear with a lower torque. All right. So we can adjust this accordingly based on the design of our transmission system. And sometimes we want speed reduction, and sometimes we want remote driving of the joint. Okay, so a lot of time you may not have the motor fixed directly at the joint. All right, so say for example, this a pulley system or belt system. Okay, you may have a joint. Okay, that's here. This could be your joint. Okay, so let me put in this sign here stands for your center of mass. Okay, so this is like your link. Okay, so if you want to move this link, okay, and this is your joint. So you want to move this link, okay, but you cannot attach your motor directly here, okay. You can actually have a pulley system, okay, or this is like a belt, okay, and then you fix your motor. Okay, so the motor can actually do this to drive your link that is remotely away, some distance away. Okay, and sometimes you want to convert the motion type, like earlier on what we see here. Okay, from rotation to linear. Okay, from rotation motion to linear motion. All right. Okay. Okay, so let's first talk about this speed reduction relationship, or rather the speed torque relationship, or how do we actually get the relationship with respect to, or rather in terms of the transmission mechanism. Okay, so say if we are looking at a simple gearbox, okay, with a pair of gears, okay, we see that there's a blue and a green gear. Okay, so although they are represented by circle, but they are really gear. Okay, so this is a gear. Okay, gear with radius, RIP and ROP. Okay, and so let's define this thing called gear ratio. Okay, so this is nothing but the ratio between the output shaft, sorry, the output gear and the input gear. Okay, so this part here is your output, and this part here is your input. Okay, so if you have your motor, okay, so you have a motor. Oh, so you're gonna send your motor here. The motor shaft, okay, maybe I will be more specific. The motor shaft is going to input a certain motion, okay, and it's going to create a motion at the output side, okay. So that part is a load. Yeah, I'll call this load. Okay, so this part here is your load. Your load, right? So this blue gear is connected to the load, okay, and the gear ratio is the ratio between their radius, okay. So the size of their radius, the ratio of the size of the radius. Okay. So how do we find the relationship between the input speed and output speed? Okay, so if we have a model at certain speed of theta dot IP, okay, let's call this theta I, theta dot I instead. Okay, it's easier. Okay, and it's going to create this output speed of theta dot O, right? And so we know that the easy way of, there are a few ways of seeing this. Okay, so maybe one easy way of seeing this is that at this point here, okay, this point here is going to have the same displacement, all right? Because they are in contact. If you contact these two gear together, okay, it's going to have the same linear velocity, right? So that say, if you have this as V, okay, so V is going to be the same throughout, okay? It's going to be I will drop the O, I will drop the P, okay? So Ri basically RIP, okay? And theta sub I or theta dot sub I, okay, is the same as your output side, okay? The same as your output side, the dot here. All right. So from here, it's going to be quite obvious that if you make this the subject of formula, okay, right, you're going to get Ri over R naught theta I, right? And if we define our gear ratio ether as RO over Ri, okay, so this is nothing but your inverse of your this gear ratio, right? So this is nothing but 1 over ether, right? Okay, so now we have this equation here, right? We have this equation. Okay, so that is the gear ratio is actually inverse of our input output speed ratio. Sorry, output input speed ratio. Okay, so what about your torque? So how about the torque relationship? And it's going to be quite similar. Okay, the torque relationship is a good way of seeing it. Let's maybe go back to the principle of virtual work. Okay, previously we looked at it, and this is one way of seeing it. You can assume that the work done, input output is going to be the same. Okay, so the power is going to be the same. Right. Yeah, let's see if we have our output. Let's put output on our left side. Okay, so it's going to be easier. The theta output. Of course, work done, you can kind of make it as power, okay, tau omega. Okay, the output side is going to be the same as the input side. Okay, this is theta dot because it's hard for me to write the dot. All right, so now from here, okay, we know that the output torque is really the inverse ratio. Okay, input output, right? And this part here we have already worked out just now. Just now we kind of look at this, right? And this is actually the inverse of your gear ratio. So now we have the inverse of it, all right? Oh, sorry. Okay, I'm putting my output on the left side. Okay, so this is your input. Okay, we are going to put output as a subject of formula, all right? So you know that this is nothing based on the relationship. This is actually the gear ratio. Okay. So now we also have a relationship. Okay. So this is how you look at it. It could be quite straightforward. I'm sure most of you have seen this. Okay. So just to make sure that we are all on the same page, okay, you can actually derive this very easily, right? But of course, the rule of thumb is kind of easy. You when you reduce the speed, you kind of increase the torque, and vice versa. And the speed is actually the speed ratio is actually inverse of the gear ratio. So whenever we have a gear there, we are going to speed down or speed up. Okay. Let me see if yeah, maybe I will skip this. Usually in actual physical class, we will have a short break time and get you to think about this. This is actually a very tricky question, but maybe we can do this another time. Let me just move on. Okay. Okay, so for the next 15 minutes or so, I'm going to just relate this into our independent joint control. Later on, we're going to model, after knowing the physics behind the engineering part, we're going to model it so that we can design the right control for this the joint controller. Okay, so when we talk about independent joint control, we are really looking at this entire manipulator arm, but isolating each of these joint and design the controller for each of them separately. Okay, so the usually I will go through the second order system before doing this, but this time around I will shift the second order system later on. Okay, hopefully if we are able to get back in person, then we will do that in class. Okay, if not, we will still do it later on online. Okay, but ultimately we are interested in uh, this robot, okay, which is essentially multi-body in nature. So the link that you have will consist of many body. Okay, okay, so you're going to have multiple input and you're going to expect multiple output if you have objective control objective for different joints. Okay, you want to make sure that all of them are met. But before looking at this actual practical way of, or rather a practical issue concern, we will first look at independent joint control scheme, where we are looking at this single input, single output. Okay, so we are looking at single input, single output. Right? So if you are just looking at one single joint, example, okay, then there is a motion. Maybe I shouldn't do this. I should do it all at the joint so that it doesn't create confusion. Okay. Okay. So now we're going to create a controller just for this joint tool. Right. Okay, so we have already gone through the various architecture, the physics behind it. And the next thing is to be able to model this. Okay, let me keep track of the time. All right, so we have seen early on the actuator, sensor, and transmission mechanism. They are sometimes assembled as an integrated uh, motor or actuator. Okay, so you have the load side and you have the motor side. So the motor and encoder, they are together already. they are already together. So the other side, you are going to expect your transmission, okay, because your load is going to be somewhere here, okay, it's going to be coupled to your load, okay. So, so the transmission is kind of like the interface between your motor and the load, okay. So later on, of course, we will move on to that. But if you look at modeling this single joint, okay, the encoder is a sensor that is going to measure the rotational speed. Okay, so now we are going to measure the resultant second order linear system. Okay, how do we actually go about doing this? Okay, we will later on go in specifically at the second order system using the mathematical equation. But let's do this modeling exercise independently first. I'm sure most of you have already done this, so it's kind of like linking it to how you will eventually use this knowledge for designing robot application or robot solution. Okay, so we're going to combine the dynamics of our electrical and mechanical system. Okay, so one part here, you're going to have your electrical system. And this part here, you're going to have your mechanical. Okay, which kind of covers your gearboxes. Sorry, your motor inertia as well. All right. So remember that we have talked about this electromagnetism, okay? And the lens force that is going to be created when you have the armature current being drawn in. So in this case, it's going to create a motor torque, okay, that is proportional to the current IA. Okay, so this part here is IA, small letter A. And you have to remember, because of this Lenz's law is going to create a oppositing EMF, okay, electromotive force, okay. It has to be in opposite direction, so it's a back EMF, okay. If not, it's going to violate conservation of energy. If you create this magnetic force, and or rather, if you create this motion and it's going to be in the same direction, it will eventually become perpetual machine. So that is not true. It's going to be opposing it, just like your drag force. Okay, it's going to oppose a motion. Okay, and so this electromotive force is also going to oppose a motion that is creating this force. Okay, so when we model this, okay, we need to know two relationships. You will end up with, if you have this armature drawing a current IA. Sorry, I changed it to capital subscript, capital A, armature. Okay, it's going to create this motor torque based on the current that is drawn. Okay, and there will also be resistance. Okay, it's not so easy. You're going to have a back EMF. Okay, that will create a motion. Sorry, that will actually be proportional to the motion that is causing this force, right? So these two relationship, and at the same time, we can work out Kirchhoff law. Okay, so these are the two physical law that we need to use, your motor torque, your back EMF, and then we will look at Kirchhoff law and substitute them in. Okay, so you know that your potential difference, okay, and the sum of all these potential difference across all these components, right? They are going to be the same as a voltage supply, okay, to it. Okay, so your voltage supply to it. Do this. Okay, let me just very quickly run this through. I'm sure most of you have done this, but for the sake of completeness, okay, each time we have different voltage in, and now we can rearrange it, okay, such that we get our equation here. Okay. Yeah. Of course, you can put in a terminology. This motor torque is proportional to the armature current drawn by a proportionality known as torque constant. Okay, for those who do a lot of mechatronic project, you know. Okay, and you have a torque constant. Sorry, this is it's not the same term. It's a typo. Okay, and then we work out the electrical side here. So electric side, and at the same time, it's going to also create motion. It is going to create a torque that will drive some loaded motion, some load to create a motion, and that part we can use this Newton-Euler equation. Okay. So this part here will be I alpha. Okay, I alpha. Right, I alpha is really angular acceleration, so theta double dot, and it's going to be the motor here, and the opposite sign I will use different color here. Okay, so you can substitute this in, and because it's going to create a drag force. Okay, here there's a drag force. Okay, there's a drag force here. And so you will also have a component that is opposing your motor torque. All right. Okay. So now you can also work out based on substituting this into your equation. Okay, let me just very quickly change the color so that it becomes clear. Okay, and this part here is red. Okay, it's gonna substitute it. All right. Okay. So now you substitute into your electrical side and your mechanical side. You have your electrical and you have okay. So I'll leave you to work this out so that when, say, if we have a transmission mechanism now, okay, so in between we actually put in a transmission mechanism. Okay, so there is now a gear ratio. Okay, you need to further put in this relationship. Okay, and then you work out the equation of motion. Okay, basically to relate the torque of your motor and the shaft motion. Okay, this is the motor part. Okay, and this is the effective loading part. All right. Okay, so I will leave you to take a closer look at this. I will upload this, of course, later on Blackboard, and then next week we will next week, if we are able to have in-person lecture, of course we will go through. If not, we will still carry on with this example online. All right, so we will also go into various control scheme when we look at the entire robot, but I will wrap up on this in our next lecture. Okay, so as not to rush you, but this example will be, I'll put this out on Blackboard, and so going through with at your own pace, try to work this out without looking at the solution, so that you convince yourself that this is derived very easily, and after that you can start working on the control scheme for this independent joint control. All right. Okay, so yeah, I will end here today so that I will not go over time. Some of you might have to rush off. Okay, so anyway, I'll be around for the next 5 minutes. So if you have any question, yeah, just feel free to let me know. And okay, so for the midterm, yeah, it is supposed to be scheduled next Thursday, but there might be some changes. Don't worry, I will give you sufficient time to have the revision on the topic covered. So it is not likely that I will include control in your midterm. Okay, so it may be only covered all the way up to dynamics. Okay, right. So if you have any question, feel free to let me know. Okay, I'm going to end this slide here. All right, so I'll be around until for the next 5 minutes. Okay, so let me stop the video recording.